Hi ladies and gentlemen, welcome to our second video on linear transformations. Today we're really talking about the fact that linear transformations on finite vector spaces are always represented by matrices. And it's the question about which matrices. The fact that that matrix is not unique lends us to the idea that it's really about the bases that we're using for our vector space. Let's jump right in. We'll take a look at what Strang has here. So he tells us about linearity, and it's important for us to understand that we can figure out what the linear transformation is doing as long as we know what's happening with the basis functions. This is really similar in the idea of what we talked about when we were looking at positive definite matrices, and we said, well, if this quantity here is greater than 0 for all x vectors, then we know we have a positive definite matrix S. However, we also can't possibly check all x vectors. So what we did is we said, well, because S automatically has, it's symmetric, so it has linearly independent eigenvectors, every x vector could be represented as a linear combination of those vectors, and hence we only need to check the eigenvectors. This is a similar type of situation that we're talking about here. What Strang is telling us is if we understand what's happening with the linear transformation on the basis vectors, then we understand everything about that linear transformation. Let's see, he goes on to talk about the matrix for T and the fact that we're always going to have a matrix. This is the part where it gets a little bit confusing, and I'll talk some about this. It comes off the rails a little bit. I have a different example, hopefully to help you understand. I think that there's a key piece of what's going on in here that's difficult for Strang to get out of Strang's text. Um, let's see, and then we'll talk about change of basis. That's all built into this, and this whole concept of similarity, which is very much in line with the similarity we talked about. In fact, it's exactly the same, and diagonalization when we talked about eigenvalues and eigenvectors. And then finally, a really important idea, which is what basis is the best basis. If we have a linear transformation and we're going to represent it as a matrix, we need to make a selection about the basis. And the question is which basis or set of basis, we have an input basis and an output basis, which bases are the ones that we want to choose? That's where we're going to finish up the conversation. All right, so the next pages assign a matrix to the linear transformation. And then as you read through this paragraph here, he continues on and says, hey, is there only one matrix? And he answers that question. He says, so the same transformation is represented by many matrices. It's just dependent upon the selection of the input and output bases. He moves on. You want to read through this, and I'll tell you about the things where I really recommend that you don't actually read because I think it's difficult to figure out what's going on based upon what he's saying. This information here has to do with understanding what's happening to the input basis. And so we can read through this. We definitely want to take a look at the example problems that he's talking about here. This is the conversation that matches up with what we talked about with symmetric positive definite, where as long as we understand what's happening with the basis vectors, we understand what's happening, period. Then he gets into the change of basis conversation here. So I will tell you, I have read this section a half a dozen times, and I still don't understand what he is saying. Um, the change of basis conversation is well handled by 3 Blue 1 Brown, video number 13. I'm going to talk a little bit more about it in just a moment here. And you know, this references Jenny's basis, and that's an important part of the course and the basics of linear algebra. What I want to do is explain what I think is the issue with Strang's conversation in this portion here. So he tells us that the input basis is going to be 3, 3, and 6, 8. But what do we know? Right? When we have the vector 6, 8, that isn't really the vector. That is a list of coefficients. We've talked about this, but it's critically important for us to keep in mind. This is a list of coefficients. And it's a list of coefficients that we take for granted because we are so accustomed to knowing that the basis is the standard basis. But the reality is, what we're doing when we write down a vector is we're writing down the representation of the coefficients given the fact that we have assumed a basis. And this idea, I can't overemphasize the importance of the concept. So we have some vector, whatever that vector might be, some u vector, and we can represent it in an infinitely different number of coefficients because it depends on the basis that we select. And we'll talk more about this. So fortunately, Strang says right here, the key, I see a clear way to understand the change of basis. Okay, let's do the clear way. The idea with our u vector is that we can represent the u vector as a different set of coefficients. And that's what leads to this easy way of understanding. And I agree with Strang. I think this is a very easy way to understand what's happening. So the vector u is what it is. Later on in the video, we're going to use a polynomial as an example because that's just a vector as long as we have the right vector space. What we're going to do is we're going to say, hey, we have the vector u, and we're going to represent it in some basis v. And when we do that, we get a coefficient vector. So c is a coefficient vector. Right? Well, let's say we want to represent u with a different basis. We're going to represent u using the w basis. And that's going to give us a different list of coefficients. And again, all of this information is well addressed in Grant Sanderson's video. So the question about change of basis really comes down to the fact that the u vector is the u vector. It is what it is. And we're just representing it differently. And what that means is that we can equate these two sides. It means that we have WD is equal to V times the coefficient vector C. And remember, you think about the coefficient vector, all it's doing is telling us what is the linear combination of the basis vectors that creates U. And that depends on the basis vectors. So if what we know, which is oftentimes the case, is the representation in one basis, and we want to know, hey, what's the coefficient vector in the other basis? It's really easy. All we're going to do is we're going to take this and we're going to come up with the new representation D as W inverse times V times C. And that's easy. That's all that's required for our change of basis. Moreover, what we're oftentimes doing is using the standard basis, which means if we're using the standard basis, this V is really just the identity, which is the representation of the standard basis vectors. And that leads to the very common understanding for change of basis where, and let's be clear about what this says. This says that we're going to take the coefficient vector in the standard basis, we're going to multiply by the inverse of the new basis vectors that have been represented in the standard basis. And what that's going to give us is the coefficient vector for the W basis. This is the whole idea. It's much easier to understand this conversation than it is to sift through this, because buried in here is the fact that we really have the standard basis. As soon as we write down these coefficients, we're talking about the standard basis, and that's woven throughout the conversation, but he doesn't highlight it. So this is a similar type of conversation, and this is good. This is a similar type of conversation right here. He talks about how do we construct the matrix for T? And what he goes through and tells us, he tells us that, hey, we know that for each input vector, when we apply the linear transformation to it, and by that I mean basis vector for the input side, for each basis vector, we apply the linear transformation, and we know that is some linear combination of the output vectors. And he says, well, that's it. I just need to know how that input vector is being converted to this set of output vectors. That's correct. But what's buried in here is the fact that it's really three things that we're talking about, not just two. And let me give you an idea of what it is. So T, the linear transformation, we have some input basis that we're going to use. And we have this representation. So think about, and let me just make a point here. The D is equal to WC, W inverse, sorry. When we left multiply by W, this is the same as saying that WD is equal to C. So when we multiply by W inverse, we are going from some other basis, which is often the standard basis, to the W basis. When we have W, that means that D is written as the coefficient vector in the W basis, and we're going to some other basis. And so what we have here is we have the input basis. We're thinking about the vectors that are going to be operated on by this linear transformation are written in the V basis. And we're going to transfer them to some middle basis where we do the operation. And that's really the part of the conversation in here that I think is difficult to understand, is the fact that we're doing some operation, some action that we've talked about previously. And then we're going to take this and we're going to transform back to our W basis. And it's not clear as he goes through this how exactly that's happening. And that's what I'm saying here is that we have a change of basis on both sides, but we cannot forget that we have the action of the operator as well. So the linear operator is doing something. It's not just transforming bases. So it's a little bit difficult to understand what's happening in here. And he gives us this key rule for understanding, but not really a clear idea of how we're going to operate with it. And so what I want to do is I want to provide you with a specific example that looks at how we do this actual change of basis. And then also talk about a practical application. So this is the basis, refresh now, this is the set of cubic polynomials. The set of cubic polynomials, P3, is equal to the span of 1x, x squared, x cubed. And this is the monomial basis. And the monomial basis is very convenient because we're used to working with this basis from when we're in our K through 12 education. But it's not necessarily the best basis. But you remember from chapter 3, when we were talking about this earlier, a lot of this material leverages what we talked about in chapter 3, as well as the change of basis information we talked about in chapter 6. So you remember that we have a way of writing the coefficients for these monomial basis vectors. Let me write down those vectors. All right, so these are the vectors looking very much like the standard basis vectors that go along with our monomial basis. So they're very comfortable for us. It's very easy for us to understand. We're going to take a look at a specific example. And let me just show you what that is. So we're going to say the z vector, but we're going to pick a vector, and that vector is going to be 1 plus 3x squared minus x cubed. So this is the vector, just like the vector u. We're going to represent this in the monomial basis. So the coefficients in the monomial basis, the coefficient vector, which is how we write things down, is going to be 1, no x's, 3x squareds, minus 1x cubes. All right. And what we want to do is we want to transition this to basis v. And basis v, I'll use the cyan. This I'm going to call Vicky's basis, kind of going along the same lines as Grant-Sanderson. So this is Vicky's basis. And what we want to do is understand how z, how the function is represented in the coefficient as a coefficient vector in Vicky's basis. So first things first, we need to write down the basis vectors using our monomial basis. Let me do that. All right, so these are the vectors represented in the monomial basis for Vicky's basis. And we can easily put these in as the columns of a matrix. And I'm going to call that matrix V. So V is going to be equal to, and I'm not going to write it out, but it is the matrix that is built with these columns. These columns certainly span the set of cubic polynomials. We can check to see that they are linearly independent, and then we have enough of them. We have 4 of them. So how do we represent the coefficient vector for 1 plus 3x squared minus x cubed in Vicky's basis? What we want to do is we want to come up with, and that's fine, I'll call it the D representation. This is going to be what we know is V inverse Z. This is going to be the coefficient vector for this actual vector, the actual polynomial, written in Vicky's basis. Let's see how we do that. I'm going to pull up MATLAB and we'll take a quick look. So I've already entered the information here. Here is Vicky's basis, and then here is the column of coefficients for our vector. And all we're going to do is we're going to define the inverse of Vicky's basis, and this is the matrix that gives us the transition from the standard basis representation to Vicky's basis representation. And then we'll just say lowercase d is equal to VI times Z. And this is the representation right here. 1, -1, 4, -5. We talked about this before. We didn't necessarily go into this much detail, but it's important for us to understand what's happening. So let's write this down. 1, -1, 4, -5. This is equal to 1, -1, 4, -5. And what we're going to do is we're going to take just a moment and we're going to validate that indeed this is exactly what we think that it should be. It's got to give us back the same vector, the same polynomial, in order for us to work. So the question we have is the f that we have up on top, the 1 plus 3x squared minus x cubed, is that equal to this representation, Vicky's basis? Well, we have 1 times the first function, which is 1 plus x, and then we have -1 times x plus x squared, and then we have 4 times x squared plus x cubed, and then we have a -5x cubed. And we can see quite quickly with 1 plus x minus x squared plus 4x squared plus 4x cubed minus 5x cubed, that's equal to 1. Those are going to cancel, and we end up with plus 3x squared and minus x cubed. So it's the same function. It's the same vector. We're just representing it differently. Now what we want to do is think about, well, what if we want to take some operation and represent it? And this is the conversation he's having up here with respect to the differentiation matrix and the integration matrix. And what I want to do is I want to look specifically at the differentiation matrix. You remember, and let me write the differentiation matrix down in the monomial basis. All right, so we've looked at this before. This is the differentiation matrix. It is the matrix representation for the linear operator of differentiation if we are using the monomial basis for the input side and the output side. And we've done examples with this before. What we want is we want the differentiation matrix for Vicky's basis. So what we are looking for, and let me change over, right? We are looking for the differentiation matrix in Vicky's basis. Well, the way we're going to do that is we're going to start with vectors that are in Vicky's basis. Then we're going to transition them to the monomial basis because we know what the differentiation operator is in the monomial basis. And then we're going to transition from the monomial basis back to Vicky's basis. So let's think about that. We're going to put a V over here because that's going to take in inputs, and it's going to take inputs that are written in Vicky's basis, and it's going to transition them to the standard basis, to the monomial basis. Then we're going to take our D, which is in the standard basis. We're going to do differentiation. And now we need to transition from the monomial basis back to Vicky's basis, which you remember is V inverse. And that's going to be the differentiation matrix, but now not monomial basis to monomial basis, but Vicky's basis to Vicky's basis. Let's take a look at that one in MATLAB. So I'll clear this out. We have the differentiation matrix that is written in our monomial basis. And what I'm going to do is call this E. E is going to be the inverse of the basis for Vicky, and then D, and then V. So this is the matrix which does differentiation in Vicky's basis. So if we feed this a vector like our 1, negative 1, 4, 5 over here, it will differentiate and give us the derivative back in Vicky's basis. So if we take E times 1, negative 1, 4, negative 5, I'll transpose that. This is the representation, 0, 6, negative 9, 9. Those are the coefficients for the derivative in Vicky's basis. And it's a really important idea because oftentimes we don't want to use the standard basis or the monomial basis. And this is kind of what he's talking about, not here. Here he's talking about subsequent linear functions. And so I'm going to hold off on that conversation for just a moment because I want to finish the conversation we're on. Here's an example. So you remember at one point we talked about Legendre polynomials. And two things about Legendre, interestingly, there are no portraits of Legendre available. He lived in the 1700s, and there are no portraits of what he actually looked like. The only thing that we have is a cartoon caricature that was drawn by one of his contemporaries. And as you can well imagine of any caricature, he probably didn't look like this at all. But it's at least gives us an idea, and I think it's somewhat humorous. So remember the power of Legendre polynomials. The Legendre polynomials, which are these polynomials here, are a basis, but this is a basis that has been created using Gram-Schmidt. We took the monomial basis, we applied Gram-Schmidt, and what we came up with was this basis. Not we, Legendre did it. And they satisfy orthogonality condition. These are orthonormal in the inner product that we have defined here. So oftentimes we want to use this basis. We don't want to use a monomial basis. We want to use the basis of Legendre polynomial. So again, let me pull up MATLAB, and maybe we're not interested in differentiation using Vicky's basis because that's just a basis that I made up. But we definitely are interested in what's the differentiation matrix when we have vectors written in Legendre's basis that gives us vectors in Legendre's basis. So I've written for, again, the cubic polynomials, I've written down the basis functions that you see here, the first 4, and I've written them in the standard basis. So we're going to build the differentiation matrix for Legendre polynomials. So this is Legendre differentiation. It's going to be the inverse of L multiplied times our differentiation matrix in the monomial basis times L. So this will take in vectors that are written in Legendre's basis and then differentiate them in the monomial basis and convert them back to Legendre's basis. This is an application of the type of thing we're talking about. Okay. This is what the differentiation matrix looks like. And we could see that it's actually quite sparse, similar to the original D. All right. Let's go back for a moment and talk about this conversation. All he is saying in here is the fact that composition of functions, when we have 2, and he puts them down as T and S. So let me pick the green. So we have a T linear transformation, we have an S linear transformation, and these are each represented, right? This is the important part. We know, and we've written about this previously, this is LA of some vector X. This is the notation that we used before when we talked about this in chapter 3. So what Strang's talking about is he's just using T. T stands for transformation. In my book, I use L for linear transformation, which is also quite common. And then I put a subscript down here to associate it with the matrix representation, which we now know is completely dependent upon the action of the linear operation and the input and output bases. There's three pieces that go into building this matrix. So in Strang's representation, he does it this way. And then, of course, he still is A times X. Linear transformations are linear transformations. They're always represented by matrices if we have a finite basis, input and output basis. So all he's saying is that when we have this linear transformation, S applied to X is B times X. When we take a look at A, B, X, and we think about what this matrix product is in the perspective of linear transformations, this is the S transformation. And so this gives us some vector y that comes out of the S transformation. And then we're multiplying by A, and that's giving us whatever our answer happens to be. And this is just the T transformation. So the composition of linear transformations, doing one transformation and then another transformation, is nothing more than matrix multiplication. And that's this entire conversation right here. Okay, choosing the best basis. What we're going to do, I'm going to move Monsieur Legendre out of the way, and we'll talk about choosing the best basis. So it's actually quite straightforward, and we've talked about this from the very beginning of the class. The best basis for square matrices is oftentimes the eigenvector basis, because that's taking the action of whatever our linear operator is, and it's diagonalizing it. And so we use this basis quite frequently. In the case where we have non-square matrices, he talks about this, right? We're really looking at the singular value decomposition, right? We're going to use the singular vectors, because not only is that a great basis, it's also orthogonal. The difference with that singular value decomposition is, though, I have an input basis and an output basis which are different, which I absolutely have to have if I don't have a square matrix, right? If I have m by n and m is not equal to n, then I necessarily have to have different bases, because I don't even have the same dimension spaces. And so we're going to use singular vectors as the best way for us to represent the linear transformation. And of course, you already know singular vectors are really eigenvectors. This is why a lot of people think that eigenvalues and eigenvectors is the most important transformation that we have for finite dimension vector spaces, is because the fact that we take A transpose A and A transpose, and we use the eigenvectors of those, and we use the fact that these are symmetric positive semi-definite matrices to come up with a beautiful set of basis functions. All right, so the other conversation that is related to what we've had before, back up a little bit, is this conversation right here where he's talking about similar matrices. We've already talked about similar matrices. Let me remind you, we said that A, if it's equal to B times C times B inverse, for all B matrices, A and C are similar. And we talked about what this means with respect to diagonalization. The reason he's using a B here is for a different basis. And this representation, again, you recall we have A times Z is equal to B, C, B inverse Z. And this is the change of basis from the standard basis into the new basis B. This is the operation, and this is the transformation back to the standard basis. And whatever the operation is that's happening here is the same operation that A is doing. It's just A is doing it in the standard basis. So the matrices A and C are similar to one another because the operation that they're doing is the same. This conversation is just turning this around exactly the way we discussed with the Legendre example. let's take a look at this, and we're going to rewrite it. I'm going to right multiply by b, so I've got AB is equal to B times C, and then I'm going to left multiply by the inverse of B, and this becomes B inverse AB is equal to C. Well, but wait a minute, that that's exactly the same as this with respect to the fact that if this is true for all B, A and C are similar. Because this change of basis, as we just discussed, is going from the B basis to the standard basis. It's doing the operations of A in the standard basis, and then this is changing from the standard basis back to the B basis. And that's exactly what he says right here. He says, we're going from the B basis to the standard basis. We're doing the operation of A in the standard basis, and then we are transforming back to the basis B. This is exactly like the differentiation matrix that we created for Legendre polynomial. Okay, another example here, worth your time to look through this example. This has again to do with the differentiation and taking a look at a different basis. This whole idea of the fact that we can represent linear transformations using a matrix is, as we discussed previously, what a lot of people consider to be the fundamental theorem of linear algebra. Right? Linear algebra is all about linear transformations. And in the case where we have finite dimension vector spaces that we are doing our linear transformation between, then those linear transformations are always represented by a matrix and matrix multiplication after we identify the bases that we want to use. And the flip side is true. Every matrix represents a linear transformation when we think about matrix vector multiplication. So questions for today, let me pull those up. All right, so here are the questions having to do, of course, with linear transformations. This has to do with the change of basis and the basis W, which I showed you in the video, but we didn't do anything with it. And then finally, this conversation about, hey, what's the best basis? What's the best basis I can use to represent the action of A? Thanks very much, and we look forward to seeing you in class.